Okay, then welcome back to the 9th lecture. Let's first recap what we did last time. So after our proof of the universal gate set, where we proved that any unitary operation on a register of n qubits can be decomposed into C0, Hadamard, and T gates. So this was, we finished the proof the last time, and then we started discussing the Fourier transformation. Okay? And the reason is that the Fourier transformation is an important building block for quantum algorithms. And last time we introduced the Fourier transformation, and then we introduced this formalism of the binary fraction. Okay? Let's briefly recall this, because our aim today is now first to finish this chapter on the Fourier transformation by finding a circuit with which we can efficiently implement this unitary, so this Fourier transformation, which is unitary, with our circuit representation. And after we found the circuit representation, it's going to be exciting, because today we then going to see our first quantum algorithm. Okay, so let's start with the recap of the Fourier transformation. So the Fourier transformation was a linear operator, a unitary operator, acting as follows. So if f acts on j, we had 1 over 2 to the power of n. So we suppose that j is now a register of n qubits. So then this normalization constant is 1 over the square root of 2 to the power of n. And then a sum k equals 0 to 2 to the power of n minus 1 of e to I to pi j k times basis state k. So it's a superposition of all basis states k, which have the same weight, but different phases. Okay? And we also introduced the binary fraction. And we wrote 2 to the power, we wrote j divided by 2 to the power of L as something like, we have j n minus 1 times 2 to the power of n minus 1 minus L plus j n minus 2 times 2 to the power of n minus 2 minus L, and so on, to j L times 2 to the power of n minus 1, this is L of 0, plus jl minus 1, 2 to the power of minus 1, and so on, to j0 times 2 to the power of minus 1, and then we have here n minus L, minus 1 minus L. Sorry, 0 minus L. Oh, n minus 1 minus L. Okay. Okay, and this we wrote as follows. So this, in the binary representation, the first part is usually written as, so this is a natural number, and we write this as j n minus 1, j n minus 2 to jl. And this part is a fraction, so it's smaller than 1, and we write it as O point jl to jl minus 1 to j naught. No, it's not an L, it's L minus 1. Okay, and altogether, you can write this as jn minus 1, jn minus 2 to jl, and then a dot jl minus 1 to j naught. Okay, the reason that I'm writing this down is because we are now going to use this in order to rewrite the quantum Fourier transformation. So it's chapter 2.4.2. And we start off from this expression, use the binary refraction notation in order to see that this is a tensor product of, that this is a product state, so to say, right? So let's start off from this. So we have the Fourier acting on J gives 1 over this constant times the sum k is equal to 0 to n minus 1, and then e to the I 2 pi j k divided by 2 to the power of n, which is missing here. Okay. And then, okay. And the first thing we do is we represent k in binary representation. So we have this constant factor, and now a sum over k the n minus 1 to k naught, which run from 0 to 1. So all these numbers k n minus 1 to k naught run from 0 to 1. And for k, we write now a sum over from L equals 0 to n minus 1 of kl times 2 to the power of L divided by 2 to the power of n. So this is an n. And then this one is kn minus 1, kn minus 2 to k naught. Okay. As a next step, we take down the sum such that we get a product. So we have here a product of L equals 0 to n minus 1 by 2 pi j kl divided by 2 to the power of n minus l. And then we have here, we write this now explicitly as the tensor product. Okay, now we see that there is exactly one such term where kl appears, and we take this term kl and combine it with this ket kl. Okay, so we get 1 over square root of 2 to the power of n. And then we have, let's write it in this way. So we have sum over k n minus 1 equals 0 to 1, and then e to the I 2 pi j k n minus 1 divided by 2n minus l with the ket k n minus 1. And then here sum over k0 equals 0 to 1, e to the I 2 pi j k0 n minus l k0. So it's not n minus l, it's here it's n to the power of 1, because we have l equals n minus 1. And here we have l is equal to 0, so we have 2 to the power of n. Okay, you now see that we already have the structure of a product state. So what we now do is we can write this down as in the notation of a general tensor product. So we continue writing this as this constant, and then the tensor product from L is equal to 1 to n. And then we have the sum of k n minus l equals 0 to 1, and then e to the I 2 pi j k n minus l divided by 2 to the power of l k n minus l. Okay, and what we do now is we perform this summation, because there are only two summands. So we have, if KNL is equal to 0, okay, then this sign gets 1. So this phase factor gives a sign of 1, and we have here 0. And if Kn minus L is equal to 1, then we have here e to the I 2 pi j divided by 2 to the power of L1. Okay. So now we use, here you see we have this factor j divided by 2 to the power of L. Okay. And this, we know how to express this in terms of this binary fraction. That's exactly what we wrote down here. So we now use j divided by 2 to the power of L from, I think this was equation 292. So this is 2.93. So now we insert this one here, Jn minus 1 to Jl, and then a dot and Jl minus 1 to J naught. And, okay, this one is now in here, and what we see is that the first part of the binary representation is the element of the natural number, right? Everything which is on the right-hand side of this dot is smaller to 1. Means everything which is on the left side of the dot gives a natural number, and we have here a phase e to the I 2 pi. And any natural number here, modulo 2 pi, can be neglected because we're having a phase. So only this term here on the right is non-vanishing. So we can rewrite this then as fj is equal to 1 over n, and then tensor L equals 0 n 0 plus e to the I 2 pi, and then O point j L minus 1 to j naught. This is equation 2.94. Okay, let's do one more line. Let's write this tensor product. So we have then, so this 1 over square root of 2, then 0 plus, if we have L is equal to 1, we have e to the I 2 pi times O point j naught. Then 0 plus, if L is equal to, we have I 2 pi, then O dot A 1 j naught. And if L is equal to n, we have 0 plus e to the I 2 pi O point j L n minus 1 to j naught 1. Okay, so I explicitly wrote it in this form of a product state, such that you can see that each factor of this product state is a balanced superposition of 0 and 1, but the factor 1 comes with a phase factor, which differs for all these qubits, right? And now remember how we get a balanced superposition of a single qubit. This we get if we perform a Hadamard, right? And this means that in order to get a circuit representation of this Fourier transformation, it's clear that we have to Hadamard each qubit, And in addition to Hadamard, we also have to perform some phase operations in order to get this phase here. And this means that already here we see that the circuit for the quantum Fourier transformation must be composed of Hadamards, of single qubits, and then of controlled phase operations, where we have only phase operations acting on a single qubit. But these phase operations must be controlled because it depends on this J0, J1, and so on, which are the values of the different qubits. Right? And we now use this expression in order to state the circuit. But let's write this down first. So this product representation suggests that the circuit of the quantum Fourier transformation must be composed of Hadamard gates which bring, or which put the single qubit into a superposition of 0 and 1. Hadamard gates and controlled phase gates, or phase shift gates. So what I'm doing the following is I'm gonna show you the circuit, and then we check that this circuit indeed performs the quantum Fourier transformation. Okay. First, let us define the phase shift gate, which is as follows. The phase shift gate RK, okay, which is the phase shift gate with a phase of 2 pi divided by 2 to the power of k. So it has this following matrix representation: e to the I 2 pi divided by 2 to the power of k. So and then the circuit of the quantum Fourier transform looks as follows. So we have here qubit implement Jn minus 1, then Jn minus 2, then we have J1 and J0. Okay. First, we Hadamard this first qubit, then we perform a controlled phase gate R2, controlled on the second qubit. And nothing happens here. Then we perform similar controls on the first qubit. So up to Rn minus 1 and Rn. Then we do a similar procedure for the second qubit. First Hadamard, and then phase operations. And then on a similar way, this is done on all the qubits. And then the second last, we Hadamard. Again, a controlled phase. And then in the end, we Hadamard the last one. And then in the end, we swap those qubits which are on the opposite side. And then we're done. So this is 2.96. Okay, that is the circuit. And in order to discuss how this circuit acts, let me do this in 3 stages. So the first stages are those operations acting on the first qubit. So it's this stage. This is stage 1, where we only have operations acting on the first qubit. And then we have the second stage. Goes to here. We have operations on the second to nth qubit, and then here in the end we have only swap operations. So I call this swap. And in order that this indeed implements the Fourier transformation, let us do the calculation step by step. we start with the part 1. So we start with n qubits in j is equal to jn minus 1, jn minus 2, j naught. And then acting with the Hadamard gate on the first qubit. So this gives h acting on jn minus 1, and then we have here jn minus 2, which is equal to okay, write it down this way, 1 over square root of 2, 0 plus 1, and then we have here jn minus 1 to j naught. This is if jn minus 1 is equal to 0, and 1 over square root of 2, 0 minus 1, jn minus 1 to j naught, if it is 1. And this we can write as 1 over square root of 2, and then 0 plus e to the I 2 pi o point jn minus 1, and then jn minus 2 to j naught. So, okay, note this factor. If jn minus 1 is equal to 0, okay, then this phase gives plus 1. If jn minus 1 is 1, then we have here something like 1 divided by 2, meaning we have e to the I pi, and e to the I pi gives a minus 1. Okay, so this flips the sign. So this is an equality. And you see that the first qubit is now in a form which we actually would like to have, right? But now there are some phases missing, so the phase is not complete yet, right? And this is what these control phase operations do now. They only change this phase here. Okay? So next, the controlled phase shift. On the first qubit, conditioned on the second qubit. Let me write this as C1, 2. So it's a conditioned phase operation R2, which acts on the first qubit and is conditioned on the second qubit. So this is the notation. This one results in the following. So I think we can give this an equation number. 2.97. And this is then, we have C1, 2, R2, meaning the phase operation R2 acting on the first qubit and conditioned on the second qubit. So this acts on this state here, which is 1 over square root of 2, 0, plus e to the I 2 pi o dot jn minus 1. So this gives now, so it's conditioned on the second qubit. The second qubit is in jn minus 2, so it's operation R2, to the power of Jn minus 1 acting on this one here, acting on the first qubit. Yes. Okay, and now this phase operation gives 0 plus, so meaning this phase operation gives a phase if the state is in 1, and it gives this phase e to the I 2 pi divided by 2 to the power of 2. So it's then e to the I 2 pi O point Jn minus 1 and e to the I 2 pi, and then we have 2 pi divided by 2 to the power of 2. And this is 1 over square root of 2, 0 plus e to the I 2 pi O point Jn minus 1, J, okay, there's factor missing, Jn minus 2. Okay, what you see is that this controlled phase gate, simply added here one more bit in this binary refraction. Okay, so this is what we got. And what you see is now, if you go to the circuit, all these other controlled phase gates, they simply act similar and add bits here in this binary refraction. So all other controlled phase gates act similarly, resulting in the following state: 1 over square root of 2, 0 plus e to the I 2 pi O point Jn minus 1, Jn minus 2 to J naught. And now, so this is the first part, right? So with this we finished the first part of our circuit, which describes the, how the first qubit is changed, right? And now the second part of the qubit, the second part of the circuit, acts similarly for each qubit, right? If you take a look here, then this is actually the very same thing. The only difference is that the number of controlled phase gates, and the number of controlled phase gates which act there, and this is similar for all these qubits. So we can now discuss part 2 to n together. So part 2 to n gives a repetition of the same procedure for qubits 2 to n, gives the following state. So we then have one, right. So this is simply the very same procedure for all the qubits. And what we get is the state, okay? And if you now compare the state with the state that we want to get, so it's unfortunately it's not on the blackboard anymore, but it was equation 2.94. If you compare it, then it's exactly the same state, but the qubits are exchanged in the sense that now we have to swap the first with the last qubit, the second with the second last, and so on. And this is exactly what the last part of the circuit does. It simply swaps them, those qubits which are opposite to each other. That's the last part. So, by comparing equation 2.100 with 2.94, you see that both circuits coincide, or both states coincide. Up to the ordering of the qubits. Hence, by swapping the case qubit with the k plus 1 minus n qubit, we arrive at the desired output. Okay, so with this we've seen that this circuit indeed implements now the quantum Fourier transformation. But okay, to finish this, let us see how many gates are actually required to implement this. So how many gates are required? So for the first qubit, we have one Hadamard, and then we have n minus 1 controlled rotations. Controlled phase gates. Then the second qubit, we again have one Hadamard, but now we have n minus 2 phase gates. So, and similarly, for the nth qubit, we have one Hadamard, which is one qubit, or one gate. Sorry, not one qubit. And then for the last part, for the swap part, we have at most n½ gates. So altogether, in total, we have n plus n minus 1 plus n minus 2 to 1 plus n½ which is n plus 1 times n½ plus n½ which is n plus 2 times n½ gates. Okay, now since by equation, or by, it was 2.26 and 2.31, there you possibly remember that we discussed controlled unitary operations with a single control, and we've seen a decomposition of the controlled unitary operation, right? And you remember that this decomposition was in terms of C0 gates and single qubit gates. And for this decomposition of the swap and of a controlled unitary gate, we needed a constant number of C0 and single qubit gates, right? So since by 226 and 231, each swap gate and each controlled unitary with a single control requires a constant number of gates. The circuit is 296 requires of the quantum Fourier transform requires a number O(n squared) of elementary gates. Which is C0 plus single qubit gates. Okay, so now let's briefly go through this again. So we checked the circuit. For the first qubit, we found that we need n gates. The second qubit, n minus 1. And for the nth qubit, we had then 1 gate. And in the end, we have to swap, and there are at most n half such swap gates. So in total, we see that then this gives at most n plus 2 times n half gates. So it's a number which grows as n squared. And by the decompositions that we found for the swap gates, so the swap gate we've seen can be implemented by three C0 gates. And then we also found a decomposition for a controlled unitary with a single control. So this gives also a constant number of C0 and single qubit gates, meaning that if we put this together, we get O(n) squared numbers of C0 and single qubit unitary gates. Okay, and this scales now as O(n) squared, which is efficient. So if compare now with our universal gate set, where we decomposed any arbitrary n qubit unitary gate operation, and there we have seen that with this decomposition process, we need in general a exponential number in n, right? And this gives now an efficient way to implement the quantum Fourier transformation. And so, meaning that if we are up to finding some quantum algorithms, we can use this quantum Fourier transformation because we now know an efficient way how to implement this. And this is all I want to say about the quantum Fourier transformation. And after the break, we are then studying our first quantum algorithm. So I see you after the break in 10 minutes. Okay, we are now set with all the tools that we need in order to study some quantum algorithms. So our next chapter is some quantum algorithms. And we're gonna discuss only a few. So there is actually a whole set of quantum algorithms that we know so far. And I'd like to stress actually, okay, that we know quantum algorithms for some particular problems. And here in this lecture, we want to see what's the reason for this speed up that we have from a quantum mechanical point of view. Okay, we are not particularly asking what this is good for. So if you want to go a bit more in this, I might recommend that you ask yourself what are the problems good for which we do have some quantum algorithms. Okay, there are indeed some algorithms which are good for some very particular problem that might not be very interesting, but it is indeed sometimes simply interesting to see that with quantum computing we can outperform classical computing. And as we will see, we know some algorithms where we can prove that we have an advantage with quantum algorithms. But on the other hand, there are also some algorithms that we know which indeed are able to solve very interesting problems, such as the factoring problem. But you have to be careful if there's someone telling you that with quantum computation you can do kind of very, very many interesting things. Okay? Here I'd like to tell you, be critical in the sense of don't trust everyone who's telling you that what quantum computing is all good for. I mean, there are many things this is good for, but in the last few decades, I'd say that on quantum computation there has been quite a hype. And this hype is going on because people are having some visions, right? And these are often visions in the sense of, okay, what we have on a theoretical foundation, if we can implement this on a real device, then we can go into these directions. But this implementation task is really a hard task to do, and it takes some effort to do it. Okay, this is a technological challenge, which in this lecture we don't care about. So here we want to really understand the theoretical foundation. And the aim of the algorithms that we study here is to see that how this works. So how does it work that we can use quantum mechanical principles in order to perform tasks which we cannot efficiently perform by classical means, right? And this now brings me to a classification of the algorithms. So I'd like to kind of classify in the beginning the algorithms into 3 approaches. The first approach, I call this a relativized exponential speedup. Okay, and this is as follows. So it's given, suppose that we are given a quantum black box, which we usually call an oracle. Okay, so you will hear the word oracle every now and then. So at some point you get comfortable with this. So simply consider the oracle as a black box which is doing something you don't know what it's doing. Okay, but you can put in something and you get something out. So suppose you were given such an oracle, and this oracle performs a unitary transformation which is a priori unknown, right? And what you want to do is you want to analyze what this black box, so what this oracle is doing, and you analyze this by calling this oracle. So you call it, and then you check how often do I have to call this such that I can analyze what's going on. And by algorithms, which we classify as relativized exponential speedup, are those algorithms with which I can analyze this quantum black box efficiently compared to a classical analyzation if I put in some classical states and get out some classical states, right? So it compares the analysis of an oracle between having some quantum inputs and quantum outputs and classical inputs and classical outputs. Okay, so let's write this down. So it's now we are chapter 2.5. So there are 3 we consider approaches. The first one we call relativized exponential speedup. So given a quantum black box, also called oracle, which performs an a priori unknown unitary transformation there are algorithms which can analyze what the black box does with exponential speedup. So I put exponential in parentheses because we are also going to see such an algorithm which gives a constant speedup. Compared to a classical analysis. So an example is Simon's algorithm. and we're going to discuss Simon's algorithm. So possibly we start today, and otherwise we discuss it next time. And then the second approach, this I call the exponential speedup for apparently hard problems. And by this, I mean that there are quantum algorithms which can solve some tasks in polynomial time, which are apparently hard classically. And by apparently hard classically, I mean that we do not have classical algorithms with which we can efficiently solve these problems. And one of these is, for example, Shor's algorithm. So these are quantum algorithms. That solve a problem in polynomial time. Where the problem appears classically hard. Example is Shor's algorithm. And we will discuss quantum phase estimation, which is at the heart of Shor's algorithm. So which, once you understand quantum phase estimation, it's easy to understand Shor's algorithm. And then the third approach is non-exponential speedup. Well, and by this, I mean those algorithms which can solve a problem faster than any known classical algorithm, but not exponentially faster. So quantum algorithms. That are demonstrably faster than the best classical algorithms. But not exponentially faster. And we also discuss an example thereof, namely Groover's search algorithm. So Groover's search algorithm is a search in an unsorted database, and there exists a quantum algorithm which is known as Groover's algorithm, which provides a quadratic speedup compared to the best classical algorithm. So let's now start with our very first algorithm, which actually falls in our first category, which is the relativized exponential speedup. And this is not providing an exponential speedup. The reason is that we are not considering this algorithm in terms of a number of qubits, but it gives us a constant speedup. But it more or less falls in this direction because it deals with a quantum black box. So from now on, I'd like to call this the oracle. And this is called, the algorithm is called the Deutsch algorithm. And it's actually, I'd say, the easiest algorithm that we have, from which we can see what the principle is behind the fact that we can perform this task faster than with the classical input. So 2.5.1, Deutsch algorithm. So Deutsch algorithm demonstrates really how we can use this the quantum superposition principle in order to perform a task faster than without this superposition principle. Okay, let's see how this goes. So suppose we are given an oracle which evaluates a function say function f with domain and range of a single bit. So with a 1-bit domain and range, according to the unitary, I call this C UF on x, y is equal to x, and then we have y in the addition modulo 2 of x. Okay, so let me briefly say something here. So what we suppose is that we are given an oracle. Oracle means there is a black box, and this black box now performs a unitary transformation, okay, which is described here by this unitary. And we don't care how this is gonna happen. So we simply consider this as a black box. We give it some input, okay? The input is x and y, and we get some output, and the output is x and y plus x, okay? And we don't care more about this black box. The only thing we care about is how often we call this black box. Okay? How often do we have to call this oracle in order to get some information out? And the information that we want to get out is whether this function f is constant or balanced. So this is the task. The task is to decide whether the function is constant. This means that f of 0 is equal to f of 1 or balanced. Meaning that f of 0 is unequal to f of 1. Okay, so this is our task. So we have this oracle, this black box. We can send in some quantum states, we get out some quantum states, and we have to decide whether it's constant or balanced. And our aim is, of course, to call this oracle as less as possible. Okay? Let's start now with the classical input. So as a classical input, what we can put in is either 1 or 0, right? And if we want to decide whether f of 0 is equal to f of 1 or whether this is unequal, well, we are forced to call the oracle twice with the classical input, right? Because we can only put in 0 or 1. In order to do this decision, we do have to call the oracle 2 times. So if we are restricted to classical inputs, get the answer, we must call the oracle 2 times twice, namely for x is equal to 1 and x equals 0. Okay. Now we can think whether we can get the answer to our question, meaning that the function is balanced or unbalanced, constant or, sorry, whether it's constant or balanced by only calling the oracle once, right? And it turns out if we can insert a quantum mechanical state, then it suffices to call the oracle once. So I wrote down that if we can input coherent superpositions, we only need to call the oracle once. Well, coherent superposition is here now the key. The reason is that if instead of using the input 0 or 1, we can now use a superposition of 0 and 1 such that this function is evaluated in parallel for both 0 and 1. And then we use some interference such that we get out our answer. And this is what we're going to do now. So we're going to now come up with a circuit such that it suffices to call the oracle once. And what we put in is a coherent superposition of 0 and 1, and then we do some interference. And via this interference, we get the answer. So let us consider the following circuit. So we start with 2 qubits in 0. Then we perform an X gate on the second qubit. Then we Hadamard both qubits. And then we perform this controlled unitary, which is our black box. And then we Hadamard the first qubit again, and then measure. So this circuit, you also find the representation. So we used for the oracle the following representation. So we put in x and y. This performs the oracle unitary transformation, and we get out x and we get out y plus x here. And then There's the Hadamard in our measurement. Okay, so this is the circuit that we consider. And what we do now is we calculate the output of the circuit. So this is number 202. And here I didn't give this a number. It's 201. So let's go now through the circuit. So the first thing what we calculate is the X gate and then the Hadamard gates. So the X gate on and the first Hadamard gates. Act as, so we have 0, 0, and then the X gate, which is identity on the first, and a NOT gate on the second, so we get 0, 1. And then the Hadamard, so we have 01 and make a Hadamard on both, so we get 1 over square root of 2, 0, plus 1, tensor 1 over square root of 2, 0, minus 1. Okay, so this is the state here at this position. So it's 2.04. That's where we are. And what we now want to see is, okay, what is this controlled unitary doing? So this is our oracle, right? So this is, let's say, here in this big box, this is our oracle, and we call this now. We call this once for this state, and let's see what happens. So next, note that the controlled unitary acts as, so suppose we act on the state, suppose we have a state x and then 1 over squared 2, 0, minus 1. Okay, so this is what we put in. We have here some state, and then tensor this, 1 over square root 2, 0, minus 1. And x simply means either 0 or 1, right? And then once we know how this acts on this state with x, then we can put this together. So let's calculate how the controlled unitary acts on this state. So as controlled unitary, UF on acting on x and 1 over square root of 2, 0, minus 1. So first, we use this. Here we wrote down how this controlled unitary acts. So we have x and then 1 over square root of 2. We have 0, O plus, and f of x. This is not correct, sorry. This must be f of x. Okay, it must be f of x because we have to find out whether f is constant or balanced, right? Sorry for that. So we get for the controlled unitary now acts as follows. So we get this minus 1 plus f of x. So which is x and then 1 over square root of 2, 0, minus 1, if f of x is equal to 0, and minus x 1 over square root of 2, 0, minus 1, if f of x is equal to 1. Okay? So you see if f of x is equal to 0, nothing happens. And if f of x is equal to 1, then we have here O plus 1 gives 1, and 1 plus 1 modulo 2 gives 0. And then we simply get a minus sign here. So it remains the same state, but we get a minus sign. And this we can now rewrite as minus 1 to the power of f of x, and then x 1 over square root of 2, 0, minus 1. It's equation 2.105. So we now have just calculated how this controlled unitary acts, and we can now use this in order to calculate the state of our circuit after this controlled unitary acted. So we use equation 2105 here in 2104. So using this equation 2104 transforms as follows. So we have 1 over square root of 2, 0 plus 1, it's this state, and 1 over square root of 2, 0 minus 1. So this is the controlled unitary. Now we use this result, so we get 1 over square root of 2, and then minus 1 f of x, f of 0, 0, plus minus 1 f of 1 times 1, and then 1 over square root of 2, 0, minus 1. Okay, so now we are here at this position. And as you can see by the circuit, we can now drop the second qubit. So we can forget about the second qubit because the rest is simply acting on the first qubit. And we only measure on the first qubit. So we can now forget about the second qubit and simply consider the first qubit state. And now what we do is we Hadamard the first qubit, and then we see what the measurement gives. So. So calculating the Hadamard on the first qubit. So we Hadamard the state here, 1 over square root of 2, then minus 1 f of 0 times 0 plus minus 1 f of 1 times 1. Okay, this gives 1/2, and then we have minus 1 f of 0, and then here 0 plus 1 plus minus 1 f of 1, and then 0 minus 1. Okay, now we can set together all terms with the ket 0 and the ket 1. So this gives 1/2, and then we have minus 1 f of 0 plus minus 1 f of 1 times 0 plus minus 1 f of 0 minus 1 f 1 times 1. Okay, and what you see now is that here we have a plus in between these two signs, and here a minus. And what you see is if f of 0 is equal to f of 1, this interferes constructively in the sense that this gives either plus or minus 2. And this vanishes. Okay? So meaning that if f of 0 is f of 1, then we are left with 0. And if they are unequal, then this one vanishes, and this one interferes constructively and gives plus or minus 1, so we get out 1. So this gives zero if, okay, I write down plus minus 0, if f of 0 is equal to f of 1, and plus minus 1 if f of 0 is unequal to f of 1. Okay, what you see now is if we perform a measurement of the first qubit, then we can decide with certainty whether this function is balanced or whether it is constant. And we called the oracle only once. And the reason for this advantage now compared to classical inputs is that we can evaluate this function with a superposition such that f of 0 and f of 1 is evaluated in parallel. And then we again performed a Hadamard such that we have an interference of these two outcomes. And the interference is then such that it is either constructive if they are equal. So this term is constructive if they are equal. And this one would be then destructive if they are unequal. Right, so we use then in the end interference in order to get out the right result that we want to have. Okay, so two ingredients for this quantum algorithm. It's the input of the superposition and then the interference. And this allowed us to get the outcome that we want to have by only calling this oracle once. So we only used a single call of the oracle. And by measuring the first qubit, we find with certainty constant or balanced. So this computational advantage is due to interference. Or is due to evaluating the oracle with the coherent superposition of 0 and 1, such that this such that f of x is evaluated in parallel for x equals 0 and x equals 1. And the recombination by the last Hadamard gate on the first qubit then leads to an interference of the alternatives associated with f of 0 and f of 1. Okay, I think this now finishes our first algorithm, and it is a good place now to stop here. And in our next lecture, which is going to be in 1 week because Thursday is public holiday. So in 1 week, we're then going to see Simon's algorithm and quantum phase estimation. See you in 1 week.